Okay, so are we live? Okay, so electrolysis. So let's move on to the last part of our review on electrochemistry. So electrolysis, which is the process of electrical energy, is used to cause an spontaneous chemical reaction to occur. So basically, if you have a galvanic cell, in which you have a redox reaction that occurs spontaneously and it generates a current, electrolysis is the opposite of that galvanic cell. So instead of generating a current through a redox reaction, we are going to induce a redox reaction by applying a current. So we are basically forcing the reaction. So that is how non-spontaneous reactions occur. If we apply energy, in this case electrical energy, by virtue of the current, a non-spontaneous reaction is occurred, or rather can occur. So for example, you electrolyze molten NaCl. So you apply here you have a vessel of a molten NaCl. So you are going to apply your electrons, or rather you have cathode iron as the cathode. Now in a normal reaction, the anode should be iron and the cathode should be the NaCl, the sodium and the chloride gases. But since we are this is electrolysis, so we are applying a current. So this is the opposite of a galvanic cell reaction. So your cathode is the iron. So you're applying energy in the cathode and in the carbon anode. You are applying current. Okay, so you have your electrolytic cell. So this is a more complicated version, but this one is a better version of your molten NaCl. So your anode and your cathode is iron and carbon. So you are applying energy, or you are forcefully moving the electrons from your from your anode to your cathode. So you have, in the oxidation side, you are oxidizing chloride to chlorine gas and sodium ions to sodium liquids, molten liquid. So basically, this is your electrolysis. So another example of electrolysis, this is water. So you are applying again this is a battery. So you are applying electrical charge on your cell. So the anode to cathode movement again of the electrons. So oxidation occurs when you have your you're oxidizing water to form oxygen and protons, and the protons to form hydrogen gas. So this is the oxidation of basically oxygen, and this is the reduction of hydrogen. So this is an electrolysis of water. So why do we do this reaction? We usually do it in electroplating. So if you have jewelries that are electroplated, this is done through passing a current to the jewelry, so that you deposit metals at the surface of the jewelry. So for example, golden plated, electroplated. So basically, that is electrolysis. So in calculating for that, usually the applications or the problems that you will encounter here is electroplating, because when you apply a current in your cell, in your electrolytic cell, there is mostly a deposit of a metal, especially if one of the reactants, or rather the oxidizing agent, or the one that undergoes reduction, is a metal. So the reduced metal is it will be deposited on the electrode. So that is how electroplating occurs. So you are depositing atoms of the metal at the surface of your electrode. The electrode is the jewelry. So you will apply a current directly to the jewelry. It will act as the cathode, and the metals will be deposited at the surface. So that's how you have electroplated samples. So calculations of that, we are just going to follow this general example. So you have a current applied in terms of in amperes or in seconds. So you are going to calculate the amount of charge that will be produced. So amperes using the current and time. And from the charge in the columns, you're going to get the moles of electrons, because the Faraday's constant gives us the charge of your electrons. So for example, the charge in columns is equal to current times time. So just multiply current and time, that's your charge. And a mole of electron has a charge of 96,500. Basically, this is Faraday's constant. And if you know the moles of electron, we will know the moles of the substance reduced or oxidized, and you will get the amount of product that will be deposited. So for example, you have a current of 1.86 ampere passing through the electrolytic cell containing a dilute sulfuric acid solution for 7.44 hours. So what is the half-cell reaction, and calculate the volume of gases generated at STP. So you have a sulfuric acid, a dilute sulfuric acid solution. This is from the previous example a while ago. The dilute sulfuric acid, this is an electrolysis of water. So we are calculating for the oxidation and reduction in terms of the oxidation of water and the reduction of your protons. So oxidation of water in the anode, so you have oxygen gases being developed, and in the cathode again, oxygen gases. And here you have 4 electrons involved, so the number of electrons is 4. So this is the balanced reaction. You are moving 4 electrons. Now here is how do you calculate it. So we are given the current from the equation, from the problem. We have a current of 1.86 ampere going on at 7.44 hours. So that means the number of charge will be, how much charge is that? So if you have a current of 1.26 times 7.44 hours, but remember, coulomb, for the unit of coulomb, that is basically amperes times seconds. So you need to convert it to seconds. So you have 3,600 seconds per hour. So you have 3.37 times 10 to the 4th coulomb. So that's the amount of charge that we have. And how many electrons will be used in this charge? So this charge, if 1 mole of electron has a charge of 96,500 coulombs, so you just convert it, you have 0.349 moles of electron moving. So this is the amount of electrons that is moving for the 1.86 amperes for this in the duration of 7.44 hours at 1.86 amperes. So this is the amount of electron that moved in the cell. So from the amount of electron that moved in the cell, from our equation or our balanced equation, to H2O to form 2H2 gas and oxygen gas, and we have a moving charge of 4, 2 times 2, that's 4 electrons overall. So let's say, for example, for every moles of oxygen gas that was generated from our equation, you have 4 moles of electron moving. So since we know that the duration of time for the 7.44 hours of electrolysis, we are moving 0.349 moles of electrons. So that is the amount of electrons that move. If there is 1 mole of oxygen for every 4 moles of electrons, based on our equation, reaction equation, you have generated basically 0.0873 moles of oxygen. And given at STP, we are just going to apply the ideal gas law. We get 1.96 liters of oxygen gas. The same goes for hydrogen. So again, you have the amount of coulombs, and this is the moles of electron. Now, why is this 2? So this is from our equation, 1 mole of H2 to form 2 moles of electron. Actually, you can just use this one, 2 and 4 electrons for 2, but still you will get the same values, whether you use 2 moles of H2 over 4 moles of electron, so that you are consistent with the final reaction. You will still get the same value, because 1/2 is the same, your 2 over 4 is equal to 1 over 2, so still the same value. So you have 1.75 moles of oxygen converted to volume using our ideal gas law, that's 3.92 liters. So that is for electrolysis. So if you have gases, or actually actual metals in grams, so you can just convert it using its atomic mass or its molar mass. So instead of using STP, this is because that is for gases, that's what was asked of us. But for normal electrolytic reaction, this is usually in terms of grams. So once that you have found the number of moles of the metals per mole of electron, you just convert it to grams. So anyway, that's for electrolysis. So this is this actually spells the end of electrolysis. But before we actually finish, so I'm just going to insert it here. So since we are talking about applications, especially electroplating, that is the application for electrolysis. So we electroplate jewelries, Actually, even other industrial materials that must have a certain metal coating, you use electroplating. Now, if electroplating is the application for electrolytic cells, the application for the galvanic cell is in batteries. So here are some examples of the batteries. This is the dry cell battery, yung size D, AA, AAA batteries that you have. This is the general outline of your battery. So what is contained in the interior of your battery? So you have zinc here and manganese in the battery. So they are actually using paste of zinc and you have manganese oxide. So the anode is the zinc and the cathode is the manganese, and they are using paste, not liquid, because of course the battery should not leak. Actually, if you see an old battery that is leaking, you should that is toxic, because you have leaching here of zinc and magnesium metal ions. So you have it's actually toxic. You need to throw it away properly. Now we have the Mercury battery. This is usually found in the old flashlights. If you have a very small pocket flashlight, that's Mercury battery. So the smaller type of battery that you have. And then you have the lead storage battery in cars. And this is the one of the more dangerous, because lead is very toxic to humans. Same goes for mercury. Mercury is also toxic. So this is the battery in the car. So they're using lead sulfate. So different applications, they are using different types of batteries. And then again, this is your oxygen fuel cell. So for the lithium ion battery, of course, it uses lithium. This is lead storage, it uses lead. So same goes for the mercury. It has mercury in here. Okay, so basically those are some applications of this. Is for galvanic cell. Galvanic cell is a spontaneous reaction. It creates a current. That is why a battery is a storage of electrical charge. Okay, so for an electrolytic cell, you are applying a current. So this is used for usually electroplating. Okay, so what other things that you need to consider for application? So corrosion is basically rusting is an electrolytic reaction. Not electrolytic, it's an electrochemical reaction. So the reaction of the iron, pag nagkakaroon siya ng rust, you have the metal iron, it becomes iron oxides of iron. So a combination of Fe2 plus and Fe3 plus. In particular for the rust, it's usually Fe3 plus. Now, bakit siya nagkaka-rust if nababasa? So if you have water there, the water acts as the cathode, the reducing this acts as the oxidizing agent for the rust, and you form a rust. Now to prevent that, either you coat it with a different metal that is resistant to rusting, or you use what you call it is a cathodic protector, or for example here you have an iron storage tank, you insert a magnesium bar near or in contact with the iron. So that is to protect the iron from being oxidized. So the one that's being oxidized here is the magnesium and not the iron. So they are using this type of protection system in usually ships, in building ships, because ships, especially iron, if you have an iron hull in ships, it's prone to it's always exposed to seawater, and it's a very strong, especially salt water. It has lots of electrolytic agents there. So it's prone to rusting. So either you, of course, coat it with paint, and or you use your cathodic protection. So you put a metal that has a greater oxidation reduction, that is most likely to be oxidized, so that has a greater reduction potential than your iron. So that instead of the iron being oxidized, your metal is the one being oxidized. So basically that's cathodic protection. Okay, so that's it for electrochemistry.